Okay, let's continue talking about Chapter 2. We left off and talked about the main climate zones that we see on the planet. Um, and let's talk about wind. And so, as we've said, as the planet heats up from the sunlight, it causes air to start rising into the atmosphere. And this helps create zones of low and high pressure. And so at the low pressure zones, we have rising air. At the high pressure zones, we have sinking air. Well, these zones actually rotate in different directions. Low pressure zones rotate in a counterclockwise direction, and high pressure zones rotate in a clockwise fashion. It has to do with the fact that in one the air is rising and one the air is sinking. And this is in the northern hemisphere. In the southern hemisphere, they move in the opposite direction. So you can see that what's happening is air is sort of rotating this way and this way. And what happens is the air moves from the high pressure basically to the low pressure zone. It doesn't move in a straight line, but sort of at an angle. And so it's really at the interface between these high and low pressure zones where you get this moving air, this wind. And so again, with those, we go back to the Hadley cells. These Hadley cells get air moving from the equator to the north and then back down to the equator, and then you have the Ferrel cells and the polar cells, and so they get air moving around, again, from these high to these low pressure zones. But also what plays an effect is this thing called the Coriolis effect. And so as this wind is moving around the surface of the planet from high to low pressure zones, the Earth is also moving underneath the air. So if we simplified it, for example, and just said, let's just say we had a big, large mass of moving air um, between the pole and the equator, okay? And so if we had a mass of moving air that was moving towards the equator, it would be moving in this straight line. That's if the planet were not rotating. But because the Earth is rotating underneath that air, as that air heads south, even though the air might be moving in a straight line, the Earth is rotating underneath it. So essentially the air is deflected. And as air moves south in the northern hemisphere, it's deflected to the left. In the southern hemisphere, it's deflected this way. And so essentially at the equator, as you see here in these Hadley cells, as that air moves towards the equator, it's deflected to the west, from east to west. Okay. Now in the Ferrel cell, there's air at the surface of the Earth that's moving towards the north, and it's deflected in the opposite direction because the air essentially is moving faster than the Earth underneath it, because as you go from the equator towards the pole, essentially the Earth is rotating more slowly. It's sort of the equivalent of a merry-go-round. When you're on the outside of the merry-go-round, you're moving faster than when you move towards the center of it. And of course, the equator is further out from the center of the Earth, so it's moving faster than when you go towards the poles. And of course, when you're at the North Pole, if someone is standing at the North Pole, they essentially wouldn't be moving at all. They'd just sort of be rotating in space. All right, so you got the wind moving from high to low pressure zones, you got the rotation of the Earth and this Coriolis effect, and it creates these major movements of air, this wind around the planet. The masses of air that converge on the equator from east to west are known as the trade winds. The ones between 30 and 60 are known as the westerlies because they come out of the west, and as you may know from observing our weather patterns, when we have storms and things like that, they typically come from the west because those are the predominant breezes. And at the poles, they're going in the opposite direction. They have easterlies. Um, and so again, looking here, these are the prevailing wind patterns that we have. They vary a bit in between the summer and winter months, um, you notice that in the northern hemisphere summer, you generally get a higher frequency of low pressure zones forming over land than over the oceans. That's because the land heats up more so in the wintertime, causing the formation of low pressure systems, whereas in the northern hemisphere's winter, you tend to have low pressure systems more so over the oceans because the oceans tend to be warmer than the land. Now again, that's just in general, and of course these systems can move, so we do get high and low pressure systems coming through here during the winter, but this is sort of the main pattern of the formation of these things. But then again, those prevailing winds, those westerlies, will move these things um, over time. And so the wind affects the ocean currents, and when we talk about ocean currents, we mostly are talking about the surface currents because the wind moves the surface water on the ocean. So because of the Coriolis effect, we have these, let's go back here for a second. We have these wind patterns in the northern hemisphere. Essentially, the wind moves in a clockwise fashion, whereas in the southern hemisphere, it moves in a counterclockwise fashion, again, because of the Coriolis effect. And so that gets the water essentially also moving in that same direction. In the northern hemisphere, the North Atlantic, the water moves in a clockwise fashion. In the southern hemisphere, it moves in a counterclockwise. And again, you see that for the most part, water converges on the equator from an east to west direction. This is why when tropical storms begin to form off the coast of Africa, they basically move across the Atlantic into the Caribbean and sometimes into the Gulf of Mexico or up the east coast of the United States. And of course, the same thing in the Pacific. Just take note that in the southern hemisphere, there's less land, and essentially there's this large rotation of air and water that just circles around Antarctica, around the South Pole. This creates some very strong wind and currents and waves down there, and as sailors have known since the days of they started sailing, when you try to sail around the southern tip of South America, you're going against that current and that wind, and that's some of the roughest seas on the ocean to sail, which is why people were glad that the Panama Canal was built, because then they no longer had to sail around there. Okay, so the wind mostly is blowing around this surface water, but you do get times when deep water mixes with shallow water, either by the surface water sinking or the deep water rising, either a downwelling or an upwelling. You get upwellings where deep water essentially is being drawn into and runs into the land and rises. And this tends to happen when you have prevailing winds that are moving parallel to the coast, which essentially pulls water away from the coast, really kind of pulling it away more at an angle somewhat. But as that water is pulled away from the coast, it has to be replaced by water somewhere else, and it's replaced by water that's coming from deeper down. We see a good example of this on the west coast of the United States because you have prevailing wind that's coming from the north, and so it draws water away from the coast, which causes these upwellings, and you can see, whoops, you can see that the water temperature, and then perhaps if you've ever been swimming off the coast of California, you know this, it's quite cool. That's because the water is coming from deeper down. And so you can see right off, here's San Francisco, just north of there, the water is quite chilly. Down in Los Angeles, it's still fairly chilly. It's not till you get towards San Diego that it starts to warm up considerably. A major area of downwelling occurs in the North Atlantic due to this thing called the ocean conveyor belt, and it's a major movement of water around the globe. This warm water, surface water, comes up from the south across the Central Atlantic, and then into the North Atlantic via the Gulf Stream. And then when it gets up there, it begins to cool down, and some of it sinks deeper down into the ocean, and then it travels down south in the Atlantic, deep in the ocean, into the Indian Ocean and the Pacific Ocean, where it is warmed up and rises, and then travels back in the opposite direction. If you ever saw the movie The Day After Tomorrow, the premise of the movie, it was based on the issue of climate change, and the premise of the movie was that a changing climate disrupted this conveyor belt such that this warm water did not come as far north anymore, basically turned around further south. Thus, this warm water didn't get up here, which caused considerable cooling in this part of the globe. It's thought that this has happened in the past and has been part of what happens with the ice ages. Now, of course, in that movie, it happened very rapidly in a matter of weeks. Of course, that's Hollywood, and in reality, it would happen on a much slower, over centuries to thousands of years. All right, let's just get started on section 3 a little bit, global climate patterns. Of course, we talked about with the equator being closer to the sun and getting more direct sunlight, it warms up more. It's those tropical climates, and that's demonstrated here. We have the average temperature for these different areas. This is just on a yearly basis what that average temperature is, and you can see it's quite warm in tropical Africa and Central America and northern South America, Southeast Asia, and it cools off as you go further north and south. Now you do notice there are some areas that based on their latitude should be warmer or cooler, but they're not. So for example, look here, Western China is cooler than other given latitudes. Look at Northern Europe. It's a bit warmer than some comparable latitudes. The west coast of South America, you can see, is a bit cooler compared to comparable latitudes. So, why is that? Well, let's go through some of the reasons that can cause a particular area to be a little cooler than it would otherwise, or a little warmer than it would otherwise be. Ocean currents. So oceans are very important, of course, in moving water around, but in moving that water around, they essentially move heat. So as that water, again, remember that we have this rotating pattern of water in the Atlantic. As this water comes across the equatorial regions, it warms up a lot. That water, some of it is transported into the Gulf, and that's why in the summer the Gulf water is very warm if you go down to the beaches there. And this water is then transported north in the Gulf Stream and heads across the North Atlantic. And so it's taking heat with it. So that's why these northern European countries like Great Britain and France and Germany and Spain are really warmer than they would be otherwise. Because if you notice, I mean, essentially France is at the same latitude as southern Canada. Britain is the same latitude as central Canada, but their climates are not nearly as cold as Canada, those portions of Canada, because of that warm water that comes up. Now, the coast of, again, these are air temperatures we're looking at. The coast, west coast of South America, so here you have this water that's rotating in this direction. So essentially you have cooler water coming from the south into the west coast of South America, which gives that area a somewhat cooler climate. And also playing a role there is this, you essentially have the Andes Mountains here, so you have some areas that are quite high elevation, which causes them to be cooler as well. So that brings us to topography. Essentially mountains with higher elevation, you're going to have cooler temperatures. We'll talk a little bit about an example of how mountains also can influence precipitation and rain patterns. Okay, we'll stop there. I'm just about out of time. We'll continue on the next video.